to send to you.
Okay.
Let's go ahead. Yes, because notice the first chapter the book I sent to you is start with the matrix, right? In which, of course, they mentioned the vector. But I think it would be more natural for me to talk about linear algebra starting from the vectors, because the vector is relatively simple compared, because got just so today we probably will focus on the vectors. Vectors that is a quantity which is just unlike the another quantity is called the scalars. So positive or scalar, probably talk about the two together. Scalar is such that they just give you the numbers, okay? While vectors have two properties that you have to describe simultaneously. So one is the direction, so the vector. So by definition, vector have the direction to be described or represent. Another is its length or its magnitude, you call it magnitude. Or sometimes just called the length of the certain arrow. And the scalar, on the other hand, just the numbers, just the number. It could be any number, could be real, could be a complex number sometimes. And so this number just, we just, at this stage, we just assume it is a real numbers. Okay, it could be positive, could be negative. So at this stage, we just assume it is real, it's real. And now, so here is that, of course, for the magnitude, we can always use numbers. So the length of magnitude is also the number, can you see? So length of magnitude is a scalar. So in this case, it's a scalar. So therefore, we can use the numbers to describe the magnitude of the vectors. And again, it is a real number, right? Now the question is, how do we describe the direction of vector? That is the issue. Okay.
Right.
Okay.
Change of basis.
Yeah, that's one way. Yeah, change the basis one way. Using the basis, rather using the basis. Another is, but the more intuitive way is to just use a graphical one. See, there's two representations. This is a definition. So this is a definition of vector. And another issue is a representation. Now, how, in other words, how to describe a vectors is basically, this is the important issue we have to discuss. So one is just use a graphic, you see. Graphical, I think you have known that we use arrows all the time. The graphical way is simple. We just denote the vectors. Say in this case, can we just draw the arrow? This is how we describe the vectors. We use arrow, then we use the arrow to describe the direction of the vectors. And so to facilitate our discussing, we just remind you that this part is called head, just like ordinary arrow. Physically, it's arrow. It's called head, and it's called tail. So so they got hair and tail. So therefore, we can describe the direction. And but the trouble is that if we just well, in this way we can talk about a lot of things about vectors. For example, we're talking about the algebra. Well, because after all, the vector and a scalar is a mathematical quantity. So when once we defined the vectors, immediately we were asked for the algebra. Okay, eventually have, for example, is how about the for rule? Because that is a concept that is a treatment we use when we're dealing with numbers, right? So once we got the vectors, we naturally were asking how to deal with the rule. So these are including the sum and the difference, and then have multiplication. Okay, and of course the division can be considered as a special multiplication.
Yes.
So we don't have, so therefore we don't have. So there are actually three of them. Now that became the issue. So that became the issue, even that we don't have to introduce another. So confined with the graphical representation, we can actually discuss these issues, right? So in this way that we don't have to consider how to describe direction. The basis you mentioned at the beginning that where we do need to describe, how to actually describe the vectors. But without this concrete basis, we can still talking about the algebra, how to do the addition, how to do subtraction. So that's addition. Yep. So today perhaps we start with this simple 4 rules of algebra as subtraction. Subtraction and multiplication. Yep.
And you're saying you can work with that without necessarily needing recourse to the idea of
no, we don't need
basis and an origin.
That's right. Like this idea, I can tell you what, by doing this exercise or the understanding, which will build our, eventually that is actually the logical way to introduce basis. Okay.
I see. Yep.
So we know that, for example, graphic is good. Graphic, we just draw an arrow. Of course, unfortunately, this type of graphic representation just is 2-dimensional, right? But once it's drawn, here is direction. You can see it's direction, right? Okay. And whether whether it's base, we don't have to mention the base. Yeah. So because vector is a standalone quantities, right? They have length, they have direction, and that's it. So perhaps then in addition, we'll talk about, that's called components. This is just, today we'll first talk about graphic representation, and then we'll go to the, components. These component representation must be based on the choice of certain bases. You will notice that, okay? So today we'll first talk about the graphic representation, and then we'll talk about components. Okay. Of course, it's not a big deal because after all, if we use this if this is A, oh, by the way, this is where we put arrow here to indicate it's different from the scalars. So this is called the scalar, and per another thing have to enter another code how to do using graphical method, and the length or the magnitude of the vector is just use the simple letters A. So this means so this is scalar. The magnitude is a scalar. Can you see?
Yes.
It's scalar. So vectors and the scalar are connected. Okay. And of course, here we can give some outlines. So when you talk about components, and A can also represent, for example, by uses components. So you have learned that before, I'm sure. But we'll talk about graphical first. So this is how to see. This is not a representation or notation, rather. Okay. So where of course we have immediately have explained what is I, what is J, and again this is we'll cover that afterward. Okay. So this is our unit. This is our basis. That's called the basis. Basis. And of course, apart from components, and we can easily jump to the another third one, which we just use matrix. It's just n times 0, or just n 0 times n. It's just one-dimensional matrix. Okay. I should say, I just simply say matrices. You know that we have mentioned at the beginning that the vectors can also represent by areas of numbers, just as ax, ay. Okay. Or sometimes we can also represent the matrix as this one. It's called row. It's called row matrices. But we will explain why we can simply take how can we simply rely on the two components to represent vectors. Okay. So let's talk about the graphics. So this is this first topic today. Secondly, if we have time, we'll cover this one. Okay. So let's talk about the first of all, let's just talk, do you remember how to find the sum? So how to find the sum of two vectors? The sum of two vectors.
Is it,
Say,
yeah, so you would
A
just
plus B, yeah. How to work out the sum of two vectors?
Yeah, so if they're both two-dimensional and it's A, B,
Yep.
C, D,
Yep.
it's A plus C and B plus D. If you know what I mean.
Can we just draw the graph? Are you able to draw the graph? Yeah, you can draw the graph.
I don't know if I can.
Can we just draw this use the two arrow to represent the two vectors here? Can you see?
Yes.
So what do we do when we work out the sum? We usually put their head, their tail together. Okay, that is the most common way to deal with the sum. Okay.
I see.
So if you there are many quantities in physics can be described as vectors. One is a force, okay? So for the common sense, if you just try to move the object, okay, from the resultant, the sum of this force will be along this direction, right? So the common sense tells us the sum of two vectors will be along this direction. Wait a moment. Oops. Okay. Can you see that?
Yes.
That's just come from common sense. If you're trying to move the object by 2 persons, you want to move the heavy object, such as a car. So that's one. That is a expected sum of two force, right?
Yes.
Because that is exactly how the sum of the two vectors is defined. In this case, what do we have used what we call the parallelogram. What we do, we just first draw a two parallel line here. Just a review. I think you have learned it before, so right? So first we draw the parallel line parallel to one vectors. And then we draw another parallel line, which is parallel to the first vectors. Can you see?
Yes.
So then by connect, the sum would be the diagonal from the common tail. That would be the sum.
Yes.
Okay? Perhaps use arrow is better. So that is how we use a graphical method to define the sum of two vectors. So if we just label them, so this is our A, and this is our B, then that would be the sum. So this would be the A plus B. So that would be A plus B.
Yes.
Okay. Now there are some variations if you want to apply this rule in practice. So the variation of this the sum rule is that can we just redo that? This time I just draw the first. This is how we draw the first vectors. Okay, this is the first vector. Now, when we draw the second vector, instead of put their arrow, their head, their tail together, we just shift this one to the head of the first vectors. Okay, and then this is very practical. This is practically used. So basically, in this way, the sum of the two vectors will be simply connect the first tail and the second head.
Yep.
So this is a way we work out the vector sum in practice. This vector A is vector B. It's vector the sum. This will be the A plus B.
Right.
Okay. Of course, this is, if you just consider this is variation derived from the first row, because after all, you can see this vector, the second vector. Can you see this one? If you just shift to the upper one, so that will allow you to work out the second method. All right. But but the more important thing is that to understand that parallelogram is a base to use to work out the sum of two vectors.
Yes.
Okay.
Okay.
Now there are other variations. For example, but the second one has also his advantage or useful advantage in this. If you ask to say, if you have found the sum of several vectors, this time I draw several of them. So you have vector 1 and use different colors, vector 2. This time, can we just put a 3? So there are 3 vectors. Now, how to find the sum of the 3 vectors?
Is it you take the tail of the A and connect it to the head of C?
Yes, good. That's right.
Yes.
That's right. You see, that is extension of the second method. Can you see?
Yes.
Extension method. That would be the sum. That would be the sum. Okay. So that's I just write down here. This is just for you, because we can go back to this notation when we study the matrices. We'll study other topics in the algebra. Can you see this is or in this case, it doesn't matter which A with B. So can we say, can call this A, B, and this is a C. This will be the sum. Okay, that will be the sum. So this will be the A plus B plus C. Okay, I give you a challenge question. If you want, if you see this kind of diagram, what can you make judgment? What kind of judgment you can make? So this is one vector. There's 2 vectors. To this different color. And another one. And oops, more. When you see this diagram, what conclusion, judgment can you make?
I suppose that their sum is 0.
Yes, very good. Yeah, good. Yes. So we can only say, yeah, that's right. That's good. So the vector sum, do you agree? The
vector sum is 0, yes.
The vector sum. So can we just say, can we just use this notation? I, can we use a footnote here now? The sum of these 2. So I from 1, how many? 1, 2, 3, 4, 5. From 1 to 5 equal to 0. Okay.
Yes. I see.
All right. So after that, then let's move to how to find the difference. We just follow the 4 rows, okay, or 3 rows rather, and same treatment to the vectors, or similarly we use this to treat the numbers. What is the difference? Can you come out with idea based on this basic row? Use a parallelogram to find the sum. In order to find difference between the 2 vectors.
Yes. So yes, if the sum is sort of lives in the middle, it's by symmetry, and the difference.
Are you able to draw from your side?
Maybe. I'm just trying to think how. Actually, how would I do that? Is there a special button I should
do you have annotate? Do you have annotate? If you shift,
yes.
Annotate, you should be able to participate. Yeah.
Yes. I'm not sure how you would draw the difference. I'm just trying to think.
I give you the hint. I give you the hint, right? So basically, you see, mathematics is like you have to. They have a fundamental rule. It's called axiom, right? Or the basic rule. and the others just logically derived from the known or from accepted axiom. In this case, what we can do, we can just rewrite this. Our objective is to find the difference. Can write down here. Our objective is to find the A minus B, right?
Yes.
But can we also rewrite it as a sum somehow?
Yes, A plus negative B.
That's right. That's how that is a trick we use to solve this problem. So in other words, we still can use the parallelogram method. Do you agree?
Yes, absolutely. So it would just mean that. Can
we just call this time can we call it the C? Can we use the negative B? Can we call the negative B?
Yep.
To C, right? So basically, we just follow this diagram here. So, before that, can we why don't we draw this? I'll just still use the same color to indicate it. So this is A, okay? Can we just draw B here? We put the B here for time being. So this is a B. We still put the B here. We put the B here. We put the B here, okay? But then we have to, in order to use our knowledge to find the sum, then we have to draw the vector, which is opposite to the B.
Yes.
So that's right. Yeah.
Okay. No, wait, I'm going the wrong way.
You are getting there. Can we move? You are using stamp. Can you pick up the tool from draw?
Oh, stamp. Yes.
No, your next the previous one is a draw. If you go to draw, you will find the second one is arrow. Okay.
There we go. I think this is our C.
Okay.
Or a negative B.
That's
right?
correct. That's correct.
Yeah.
That's correct.
Right. So
if you want to label them, then this will be this is A. Can you see? That would be the A. Yep. And this will be the B. And this will be our C or negative B, right?
Yes.
Now forget about this B. Now can we find the sum of A plus C by use our parallelogram method?
Yes. So we would want first do a parallel here.
Yep.
Yeah. Oh, that's not very good.
Okay. Well done. Yeah. If you can participate, then it would be more effective. Yeah. That's parallelogram. Yeah.
We come out here.
Yeah. That's correct. That's right. That would be different. Okay. Do you agree? So that this one will represent A plus C. You agree? Or A minus B. Okay.
Yes.
A minus B. So in this way, we found that one. Just makes life easier. Can we just do some parallel shift? So if that is a sum, okay, use your color. So this is a difference. We agree? Do you agree?
Yes.
Now let's do some translation. Can you see? Can we translation this arrow to here?
Yes.
So
and that is
yes. So we we follow the rule, but we end up with here. Can you see?
Yes. Okay, similar. Okay. Yes.
That's a similar. So what conclusion we can make?
That you
can we say this is exactly what we're looking for?
Yes.
Does it make sense?
It does, and it's head to head.
Yeah. So in this world, they just in general, this is a process. Okay, this logical process. So eventually, we will obtain this more similar diagram to the sum. You will notice that, for example, if we use the same colors, so that will be the first. This will be the first. This will be the first vector to be subtracted, and the second one. Second one, use green colors. So this is the second one, okay? And the difference will be this one. Can you see? The head?
Yes.
Head to head, okay?
Head to head.
Head to head to be A to be subtracted, okay? So that is I think that is important graphic representation we were going to use, and to dealing with this vector sum and vector difference. This is very useful. I will tell you some application, one of very important application. So can we just write down here? So that is how we work out the difference of two vectors graphically. So that is A, this is a B, that is B, and that would be A. That would be different, A minus C. You see.
Quick question.
Yep.
Why is the vector A plus C and A minus B, aren't they the same? Why is A minus B?
Yes, right. Yeah, they are the same because we noticed that we didn't change the direction. We didn't change the length. Can you see?
Yeah. So
we it's called, in physics we call it translation. You just transport translation. So we didn't touch anything. You see, that's how we reserve that the two quantities of the given vector, direction and length. So we can make this conclusion.
Yep.
So this is very important because you see, when we so I will give you an example. Okay, when we you probably have learned the linear equation, right? The linear equation is y equal to mx plus a constant.
C. Yep.
Yeah.
Yep.
But now we can do some abstract description of straight line. Now, can you see? If I draw a straight line, if we want to describe this straight line, what can we do? We don't have to use this coordinate. Okay. So what we can do? Can we just put the vector here? Can we put the vector here? So this vector, we just put the vector here from any point. Can we see? I just use this vector to describe it. Okay. The direction of the vector will allow this point move along the straight line. Can you see that?
Yep. Yep.
Or backward. Can you see? So in this way, they can span. So its span is just a complete number along this straight line. You see?
Right. And to describe that that line, are you saying the vector? All you need is one vector to describe the direction, and then some sort of scalar to describe
the position,
the span, or the magnitude,
or the distance from this, the distance from his tail, the distance from his tail. So in other words, if we just put the number here, can you just use this one? So this straight line can be fully determined by one vector. In this case, can we call this A? Or can we call this B? What can we call it? Any vector, can we call this a B? And the only difference is that after a while, their distance will be changed. The length will change. So what we do, we just multiply the constant. Can we multiply the K? K is just constant. So K is a scalar. K is a scalar. K could be negative, could be 0. It's a scalar. So therefore, if K is determined, and any point on this straight line can be determined relative to this reference. Can we call this a reference? Can we call this can we say this reference is R? This is reference position R. Of course, that is based on the fact that this is a reference we used. We know the reference, we know the straight line, so that we can choose a particular point R as our starting point. Now the question is that if we don't know that, what would happen? Then we just introduce another vector to describe the reference. In this case, for example, can we just use a vector? Can we use different colors? Can we use a vector to describe the R? So this vector is purely introduced. It's merely introduced to describe the position R, which is fixed on the straight line. Okay.
Yes.
So that is how we introduce. This is if the reference is not on the straight line, we can always use. Can we call this position O?
Mm-hmm.
By the way, this O could be used as our origin of Cartesian coordinate later on, okay? But at this moment, we just use vectors, okay? Now, understandably, so the position, now once we define, this is where we can define this position we can use as a reference. So therefore, how do we describe the position B at any moment?
By varying K. So
by varying K, so the consequence is that we will notice this vector. Can we introduce another vector which will be, so this is another vector, can you see? So this is when K equal to 0, do you agree?
Yes, yes.
That, and when K is positive, can you see this vector change, can you see?
Yes.
Okay.
Yep.
And also, of course, K, if the K is negative, they just go that direction, can you see?
Sure, yep.
So in this way, the red color, the third vector introduced, can be used to fully describe the straight line in space. Can you see that?
Yes, yes.
So this is in arbitrary position. So when K can be any number, K can be any number. So if you want to write the vector equation to this one, so what can we do? We just label them. Can you see? This is called B. Can we call this is A? Can we call this Can we call this R? R for just for argument's sake. We just for sake of argument, we just introduce R to represent R point. Okay.
Yes.
In relation to the O, which we know. Okay. So this vector, or I don't use R. R is very useful. Can we call it something else? Can we so call this A? This point is A. I use A. I will call this is R because R is used to describe the position.
Sure.
Okay.
And A plus B equals R.
Yes. So what is the equation? What is the vector equation for this straight line? You just mentioned it. Yes. So basically what we need to know is looking for the R, because once R is known, it's called the position. R is called the position vector. So both A and R is called the position vector.
I see.
So what is relation? Yeah, you have known that. What is R in terms of the vector sum?
It's A plus B. Yeah.
A plus
vector sum of A plus B.
KB plus KB.
KB.
Yes, KB. Okay.
Ah, right. And it's
makes sense.
It's like.
So that is a straight line. You see, this is a straight line. You see, this is very abstract straight line. Okay, in vector form. Okay, this is straight line.
Right.
Okay, it's called a line equation. It's a line equation. Can you see?
Yes.
Okay.
And is that similar to that K, that scalar would be equivalent to the sort of M
gradients
in a Cartesian line?
Yeah. That would be the gradients. Yeah. K will be the gradients.
Yeah. Okay.
So that is application of using the vector language. We use a vector, we can describe the straight line without use Cartesian coordinate. Okay. Of course, yeah. So this is important takeaway from this page is that this everything starts from here. So we only this kind of consider as axiom here. So basically, you have to remember how to find the sum of two vectors. Do you agree? And these also.
Is my internet okay?
Yeah. Sorry.
I was just checking that my internet was okay and not crappy. Okay, sorry, go on.
Okay. Yeah. So that is important thing. So let's just redraw this diagram here. So they were talking about, we just redraw this diagram before we go further. So basically that we have obtained that, we see that the sum how to describe the sum of two vectors. This is the diagram we use. 2 is 1, and the sum, and I'll just draw the parallelogram here first. Oops. Okay, that's the parallelogram. Oops, realistic. Okay, the sum will be the 2. So that is a basic. One moment. Okay, that's better. That is a sum. Okay. So they have two implications. They have two implications. Can you see? One is that we can argue this is two. We are talking about the concept of components now. So can we call this A? This is B. Then this is C. Okay. So in this diagram has two implications. So implication. Oops. So first one, we say that the A plus B equal to C. Do you agree?
Mm-hmm. Yes.
Similarly, we can see C is equal to A plus B.
Mm-hmm.
So you can interpret that as two things. So if in order to given the two vectors, we can find the sum. On the other hand, given the vector, we can find the two components. Makes sense? That makes sense?
Yes.
So depending on how you talk about that. So in this case, in this way, so A and B is called components. You see? So A and B are the components of C.
Yes. Of
C. As if that A and B belong to C, all right? Originally belong to C. Just for the convenience, sometimes we have to rewrite the given C in terms of A and B, okay?
Yes, yes.
So in the first sense, C is unknown, right? C is unknown, as if C seems is unknown here. So C is to be determined. C is to be determined.
Yes.
Okay. So this is a special case, but did you notice that in this case, these A and B are not perpendicular? So that is another. There's two implications. Another is how to say the. Perhaps we have talked about the. Yes, let's talk about the dot product first. Okay, dot product. Well, when you're dealing with the third row, which is a multiplication, then the first form is called the dot product. So actually there are two types of multiplication. So there's a multiplication.
I've forgotten what the difference is between the dot product and the cross product.
Yeah. Multiplication of two vectors, Yes, we can review that, two vectors. So one is called dot product, one is dot product. Another is called the cross product. So notation for this one is A dot B. That's the notation. And the cross product is A cross B. And in the cross product, you get a new vectors. And in the dot product, you get scalars. A, B, and the cosine theta. Okay. So let's talk about the dot product first. The dot product is such, we have two vectors. If you're looking for the dot product of two vectors, again, we just put their tail together in this case. And then we have to talk about what we call the projection. Projection. So there's a related concept is that projection. So first we have to know what is a projection. Projection can be, involve two vectors, okay? For example, if this A, projection of A over B will be just as you can imagine that this is light ray coming downward, perpendicular to the B. So you can imagine there is a direction here. That's called projection. Can you see? They just like the sound waves come downward or perpendicular to the B. Can you see that?
Yes. So it will always create a right angle.
Yeah, right angle here. That's right.
Yep.
So in this way, we can form the right angle triangle here. We can right angle. Can this is perpendicular, right? Now the projection is just this part, the length of projection. In general, the projection is also the vector. Okay, but can we just call the P? But in general, the P, the magnitude of the P will simply equal to the A cosine theta. So if this is theta. Okay. So that is a projection. So this is called the projection of A, the projection of A onto vector B. Okay. Now, similarly, you can also define the projection of B over A. Can you see? So what we can just draw the diagram here, side by side. So this is A, and so this is a B. It is B, right? And make sure it's not too big, not too short, too long. So in this way, you can imagine that there is a direction perpendicular to A. In this case, perpendicular to A. So that projection is a very important concept when we study linear algebra. So if you can imagine this is a straight line, can you see perpendicular to the A? So in this way, you got the notation of this projection. In this case, again, this angle between the two vectors is theta, and this is right angle. So this is A, this vector A, this vector A, this vector B. So this is projection. Can you see? The projection, if I use color, if I use a different color, this projection is here. That will
the projection.
Yeah.
Question: If the projection P is a vector, what direction?
Well, depend. That will be the second vector.
Okay.
The second vector. Okay. Now again, because you have learned that, so can we just write this one? So basically, the projection of the P. So this is just the magnitude, right? But how about their direction? So as the vectors, we have this magnitude, okay, and we also have defined direction. So what can we do is what we just take this direction B, which is direction of B, and immediately multiply its divide by its magnitude. That gives you definition of this projection vector.
Yes. Right.
Or alternatively, if I read this way, probably you can follow me. Can we call this called the unit vector? Can we just call this unit vector? Can we just call this the just call the B? So B is called the unit vector. Unit vector has such property that its magnitude, the magnitude is a unit.
Yes.
Can we just say B defined by the B vector defined by divided by its magnitude?
Yes. Okay. Right.
Now there's another way to rewrite the B. So B is just the scalar B, the length multiply its direction. Do you agree?
Yes. Yep.
So in this way, we just return to the B. Can you see?
Okay. Yeah. Yeah. Okay.
Think about it. So basically, so the unit vector is sometimes is used to as, or it's called the directional vector. So the unit vector is also used as a directional vector, often used as what we call the directional vector. Directional vector. So there's some idea we have taken away today. So that is a unit vector. So what is unit vector and what is a directional vector? Directional vector is very useful, which is actually the base. Eventually you will know it's actually the base, which can use to build the base, depending on the dimension of space. For example, if for the 2D, like we discussed here, it's a two-dimensional space, then we use the two-directional vector.
Yep. Yep.
In this particular unit vector, we simply use this unit vector to describe the direction of the B, vector B. So in general, any vector like this one can be written as his magnitude and multiply his directional vector.
Yes. Okay. Right.
It makes sense. So that is an important thing to understand the multiplication. This actually, when we talk about the multiplication of two vectors, perhaps we have added something. This is very important concept. So when we talk about multiplication, we have to first discuss the product of scalar of the vector of a vector and a scalar. So when you're trying to build in the how to say, when you're trying to comprehend, understand the product of vector, this is special case. So we have known that before. For example, when we discuss the straight line, where we introduce the Ka, right? Kb, do you agree?
Yes.
So in this case, K is a scalar. So K is a scalar. K is a scalar, right?
Yes.
Which can be negative.
Scaling up and down.
Yeah, it's positive. So basically, if you multiply scalar, then in this way we can try. We can build any vectors. So any vector, like in this way, can we call A? If A equal to Kb, then in other words, you just take the unit, take the direction. In this case, or another important thing is that in this case, we can argue that A and B are parallel. Doesn't that make sense? Because, no matter what K is, and the direction is always the same. The direction of these two vectors are always the same.
Yes.
Makes sense?
Yes, that does make sense. Yep.
Okay. So that is a projection vectors before we discuss the dot product here. And the dot product is simple. Can you see? This is in this first example, we only discuss the projection of the vector A onto the vector B, okay? But you will notice that the projection on A over B is also always the same. Can you see? This is can we just go to next pages? So that's then we'll talk about projection of vector A onto vector B. And we can also discuss a projection of vector B onto A. So how do we say that? That's how we define that. So basically, that will be the we know that we're projecting from first one. We know that will be simply equal to the A cosine theta, right? Cosine theta, and that is then multiply the direction. What is direction of the B? That's the B divided the B magnitude.
Yes.
Okay.
So would this be B cosine theta?
Yeah, that's B cosine theta. Can be B cosine theta, and A.
Yeah.
And A amplitude.
Yep.
So that is the only difference. The direction is different. Okay. So if we know that what is projection, then we can just define the dot product. Of two vectors. So we have A dot product B by definition is just simply equal to A magnitude A multiply magnitude B and multiply the cosine theta.
Yep.
So which is a scalar now? Can you see? It's not a vector anymore.
Yes. Okay. Yep. No, I'm with you.
You get with me? Yeah, that's a dot product. Yep. But another thing we have to mention is that this is a special case. This is parallel in this case. We just return to this diagram. These are special case. So in general, if you have it is a general case. If you can follow the we can use a parallelogram. So basically, it's A, and I can get the B here, and then the C can be considered as a sum. So this is can you just draw this diagram quickly? And that is A, the sum will be the C. It will be C, right? So in this case, A and B are not perpendicular, right?
Yes.
So in the spatial case, you will notice that we will just consider the spatial case when the two vectors are perpendicular. In this particular case, that's very important concept in linear algebra. So when the two vectors, if we just choosing, because when we choose the components, if we just consider the second implication, we will consider this C is made by two components, right? Now these two components, and as soon as they obey what we call the sum rule, or to be specific, is just use the parallelogram to determine these components. And this is a special case when the two components perpendicular to each other, can you see? Just to make sure.
No projection.
Yeah, then they will put all the ideas together after today's talk. You can put all these ideas together. So in this case, can we just consider C is divided into two perpendicular vectors here. So can we say this is A, this is B, this is C. Now in a special case, can we just choose to say can we just call the A prime, or Can we just slightly different A and this B just means it's different. Just means it's different from the previous A and B, you see? Yep. But it's the same vectors, same vectors. In both case, C is equal to the sum of these two choosing components, right? So does this one. So C will equal to A prime plus B prime. It's just different vectors. However, in this case, the angle here, the angle between the A and B are 90 degrees. So this is an important concept here to be discussed. A and the relationship between the B are we call the orthogonal. Orthogonal. Right. Have you heard of that?
I have, yes.
So that is a very fundamental idea in building the linear algebra formulas. So in this particular case, A and B are orthogonal. Orthogonal, they are perpendicular to each other. Okay. Now give you a test. Well, so what would be the case in this? How about in this case? In this case, which implies that what is the product? Dot product and A and B.
Right. It is. Well, it'll be A B cos theta.
A B cos theta is what is theta in this case?
And theta will be what 90 degree?
90 degree.
No. Yes.
It is. It's 90 degree. Yes. So what is 90 degree of cosine theta? Or half pi? If you want to review that?
Yes, half pi. Yes, half pi. Yes.
Yeah. What is the number? What is the value for this special angle, cosine 90 degree?
Yeah, this is perhaps a trigonometric review could be a good idea at some point. Yeah.
Yes.
I'm not sure.
Yeah, it doesn't matter. Yes, we can just we can review some of them on the way. We don't have to discuss the trigonometry separately. Yeah, I give you some ideas. So basically, when you study the trigonometry, you have it's useful to use a unit circle. When you use unit circle, you can define the cosine theta. So this is how do we define the cosine theta by using unit circle? Unit circle implies that the radius of the circle is unit, right? So in other words, if you draw the straight line here, if you draw the triangle here, I draw a triangle here. So this is right. So this is always unit. Can you see the radius always unit? So if you just pick up this particular angle here, so this angle is around 45 degrees, 30 degrees around, right? In this case, so you can always draw the triangle here, right angle triangle here. So this is our theta, okay? So by definition, this is 1, you see? And in this case, because this is x and y, so the coordinate here will be x and y. Can you follow me? So in other words, these lengths will be x, and the vertical one will be y. Okay. So by definition, you just check, we can review next time, cosine theta will equal to adjacent over the hypotenuse. That's definition.
Yes.
So
yes.
I draw this diagram here. So if you I can visualize this one. So I just use straight line. Okay, this is the theta is about 30 degrees. Okay. In other words, so if the theta equal to 90 degrees, what would be its x coordinate? X coordinate. This coordinate
would be
1.
0.
Yes. Okay. 0.
Yes.
So what can we conclude? What can we conclude?
That cos theta is going to be 0 divided by 1, which is 0.
It's 0. Good.
Yeah.
I think your math is good. After a few years of working, the math is still okay. I say that's good. Yeah, so that's important. Okay. Now this is very important. So okay, today probably just if you can remember this one. Of course, we're going to repeatedly using these results to study the topics. So this is something important to take away. Is this that you will? I will just use this. Can just say. So we have introduced a very important concept in the linear algebra now. When two vectors are perpendicular to each other, their dot product is 0.
Right.
Okay? Their relation is orthogonal. That's it.
Gotcha. Easy.
So
yes.
Okay.
That makes sense because the projection is non-existent. So
yes,
and then you're scaling a 0 projection.
That's right. So next week we'll continue of this particular scenario to introduce the components. Okay.
Yes.
Of course, the component can be not perpendicular, but in this is a special case. We're going to use this as a definition of the components.
Yep. Excellent. Would you recommend any chapter? Is there a chapter? Because I had a look at the book. Is there a good?
Well, I think
the vector chapter.
At the sixth moment, what if you have time, you can copy this note into your notebook. Okay, instead of keep them on the computer hardware. Okay.
Yes.
So that would be the homework. Okay. Now because you don't have to go to if you have time you can read but you can wait because today is just introduction or chapter 0, not chapter 1. Chapter 0 to the linear algebra because I think this is a natural way to introduce matrices. Okay.
Sure.
Of course we know that one of the representation would be matrix. I mean the vector can be treated as a special form of matrix, but that is just after the generalization of this basic idea about the vectors today.
Sure.
Okay.
Excellent. Thank you very much.
You're welcome.
Great.
Okay, I will stop here and we'll continue to discuss. Okay.
Next week. Okay. Thank you very much. I'll talk to you then.
Oh, by the way, have you saved this have you saved the note?
Sorry, can you I've got this one. Could
you
go
can just
back one?
save. You can just save the note. I think you can save the once. Can you see that? Can you see that they have the
Yeah, I never found it. Annotate, hide
that
video
is
panel,
that is
side by
no
side.
another tool. The toolbox you choose in the draw, stamp, spotlight, eraser format, undo, redo, clean, and then save. Save. Okay.
I got it. Okay. Screen save. Awesome.
Screen save.
Yes.
Okay. So just in case, if you haven't, I will send it to you. Okay. If you haven't.
Okay. Thank you. Okay. Thank you very much.
Okay. See you next week.
Okay. See you next week. Have a good day.
You too.
Bye.
Bye.